to everyone. Today's session we will discuss the Lagrange's interpolation function. So here the Lagrange's interpolation function is used to find out the shape functions if the elements having higher order nodes. Okay. If it is a simple nodes, if it is simple element which is having only corner nodes, then easily you can derive the shape functions in global coordinate system and natural coordinate system. If the element is having a more number of internal nodes, then the element becomes higher order element. So that for higher order elements, if it is having a more number of nodes, then the easiest way to find out the shape function is by using the Lagrange's interpolation function. Now we can see the Lagrange's interpolation function for the one-dimensional case. So in Cartesian coordinate system, you can write the Lagrange's function Lk of x, which is equal to pi, I which is equal to 1, I which is not equal to k, n x minus xi divided by xk minus xi. This is in Cartesian coordinate system, where I which is not equal to k. Here, whatever the shape function we need to find out at kth node, okay, that must not be equal to the I. Okay, then only this Lagrange's function we can use, or it is going to be applicable. Similarly, in natural coordinates, you can also write Lk of zeta, which is equal to, in natural coordinate system, I n I, which is equal to 1, I not equal to k, zeta minus zeta I divided by zeta k minus zeta I. This is in natural coordinate system for one-dimensional case, where Lk of x and Lk of zeta produces the Lagrange's interpolation functions for only kth node. Okay, where we required the shape function that is at the kth node only, we can use these functions. Now, xi and zeta I denotes x and zeta coordinates of ith node in the element. Now consider a Lagrange's interpolation function for a two-noded bar element. Okay, the two-noded bar element you can see here, which is consisting of two nodes, node number 1 and node number 2. At node number 1, value zeta value is -1, and zeta value at node number 2 is +1. The displacement at node number 1 is u1, and displacement at node number 2 is u2. And the x, which is going to be vary in the along the x direction. Okay, that is x is the variable here, and x value at node number 1 will be x1, x value at node number 2 will be x2, so that x2 minus x1, which gives the element length. Now we can consider this, the natural coordinates at any point x can be represented zeta, which is equal to 2x minus xi divided by x2 minus xi minus 1. Okay, so this we have got by using the natural coordinate system, a shape function along with relating with the global coordinate system of shape function. This is global coordinate system shape function for one-dimensional case, and this is a natural coordinate system shape function at node number 1. Okay, as taking the relation of both coordinate system, then we can relate like this. The relation is given by this is, okay, zeta, which is equal to 2x minus xi divided by x2 minus xi minus 1. Okay, so the shape function of the one-dimensional bar element is found by using the Lagrange's polynomial in natural coordinate system we are going to discuss now. We can also find by using this equation, that is in global coordinate system also, for the two-noded element. Now, for the two-noded element, n becomes 2 because there will be a two nodes. Okay, but at kth node we need to find out the shape function, so that k will be equal to 1. So that by using this equation, L1 of x, L1 of zeta, which is equal to n1 of zeta here, L1 zeta, which is equal to L1. So the shape function it is going to be used, so that n1 zeta, which is equal to zeta minus, in place of I, it is going to be 2, in place of k, it's going to be become 1, because at kth node we need to find out, so that if we want to find out shape function at node number 1, that there the k will be equal to 1, so that remaining nodes in the element that will be equal to I, so that second node will be equal to I, so that the equation becomes like this, zeta minus zeta 2 divided by zeta 1 minus zeta 2. Now substitute the values of zeta 1 and zeta 2. In the element, we know that the zeta, which is going to be vary from -1 to +1. At node number 1, it is having a -1. At node number 2, it is having +1. As we substituting zeta 1 and zeta values, we can get the equation like this, zeta -1 divided by -1, which is equal to -1 divided by 2, zeta minus 1. So this gives the shape function at node number 1 by using the Lagrange's interpolation function. So this is the same equation we have got in the natural and also even in the global coordinate system. Similarly, at node number 2, so here k becomes 2 because at node number 2 we need to find out at kth node. So L2 of zeta which is equal to N2 of zeta which is equal to zeta minus, here at node number 2 we need to find out shape function so that k becomes 2 and high will be, the remaining node will be 1 so that high becomes here 1. So the equation you can write zeta minus zeta 1 by zeta 2 minus zeta 1 which is equal to zeta plus 1 divided by 2. Okay, so this is the shape function at node number 2. So this is the same thing we have got in the global and also in natural coordinate system. Now n1 which is equal to 1 by 2, 1 minus zeta at node number 1, and n2 which is equal to 1 by 2, 1 plus zeta at node number 2. By using the Lagrange's function, we have got the shape functions at node number 1 and node number 2, and the variation of shape functions at node number 1 when n which is equal to 1, then it is going to have a value so that from this value so it is going to be varies to the node number 2 as it is going to be decreases. Okay, as you substituting the zeta values at different points, it is going to give a 0 at node number 2 and it is going to give 1 at node number 1. Similarly, at node number 2, as you substituting zeta value is plus 1, so that plus 1 again if you substitute as it is going to be give 1, so that at node number 1 the n2 value will be 1 and again it is going to be decreasing towards the node number 1. This diagram which gives the overall the shape function at node number 1 and node number 2 for the two noded element. Okay. Then the Lagrange's interpolation function for higher order elements. If the elements having a internal nodes, this is only two corner nodes, it is having the elements so that it is two noded, a simple element. If the element having the internal nodes, so that the elements is also called as a higher order element. If it is higher order elements having, so then how the shape function is going to be derived, that we are going to discuss now. The shape function of three noded bar element, now we are going to consider three noded bar, also you can call it as quadratic bar element. This quadratic bar element shape functions is going to be determined using the Lagrange's interpolation function in natural coordinate system. That is most important. Lagrange's interpolation function we can use in global and also in natural coordinate system. Now, three-noded bar element as shown in the figure, the shape function will be in quadratic in nature, see, which is having node number 1, node number 2, node number 3. So, always the corner nodes first going to be defined, then the internal node. So that this becomes node number 1, then this the corner node will be 2, then internal node will be given the number after the corner nodes. So that it having a order of 1, 2, 3. As node number 1 it is having a zeta value minus 1, node number 2 it is having a zeta value plus 1. At center it is having, because the element must be discretized with the equally spaced distance. Okay, so that at the center of this element it is going to be located the third node, so that the zeta value will be equal to 0. Then the variable x, it is going to be having a variation at node number 1 is x1, at node number 2 x is equal to x2, then the difference always which gives the effective element length. Now considering the Lagrange's function Lk of theta which is equal to pi I which is equal to 1, I will not be equal to k, then zeta minus zeta I divided by zeta k minus zeta I. This is the equation we are going to use. But this is having a three nodes, okay, three noded quadratic bar element it is, so that n becomes 3 here. Now consider first we need to find out the shape function at node number 1, so that k which is equal to 1. Okay, then n1 of zeta which is equal to, in place of k it remains with 1. Okay, and it is having along with the kth node two more nodes are there, that is node number 2 and node number 3, so that the equation becomes like this. Okay, so zeta minus I becomes here 2 divided by zeta, here k becomes 1 minus zeta 2. Similarly, for the second node, zeta minus zeta 3 divided by zeta 1 minus zeta 3. Okay, then substituting all these values, zeta minus zeta 2 is plus 1, so that substitute the here value, and zeta 3 is 0. As we substituting zeta 2, zeta 3 values along with the zeta 1 value, we are going to get, and after simplifying, we are going to get n1 zeta, which is equal to zeta into zeta minus 1 by 2. This is the shape function at node number 1 for 3 noded quadratic element. When k which is equal to 2, we need to find shape function at node number 2, then n2 of zeta, which is equal to, again here in place of k, we need to find a kth node, so that k becomes 2 here, then remaining nodes will be 1 and 3, then I will be equal to 1 and 3, so that as we writing the equation, it becomes zeta minus zeta 1 divided by zeta minus zeta 1, zeta minus zeta 3 divided by zeta 2 minus zeta 3. Then substituting zeta 3, zeta 1 and zeta 2 values, then the equation will be like this, and as we simplifying, we are going to get n2 of zeta, which is equal to zeta into zeta plus 1 by 2. This is the shape function at node number 2. Similarly, at node number 3, we need to find the shape function, then the k value becomes 3. Okay, so n3 of zeta, which is equal to kth node will be third node. Okay, then the remaining nodes will be 1 and 2. So the equation will be zeta minus zeta 1 divided by zeta 2 minus zeta 1, zeta minus zeta 2 divided by zeta 3 minus zeta 2, which is equal to, again substituting zeta 1, zeta 2, zeta 3 values. Okay, zeta 1 value is minus 1, zeta 2 value is plus 1, zeta 3 value is 0. Substituting, we get n3 of zeta, which is equal to 1 minus zeta square. This is the shape functions at node number 1, 2, 3 for 3 noded quadratic element, and the shape variation will be like this. Okay, when n1 which is equal to 1, then the shape variation will be like this. The n1 shape function, which is equal to zeta into zeta minus 1 divided by 2. Okay, so if you n1 value and how to get 1, then the zeta value, if you substitute at node number 1 as minus 1, then you are going to get n1 value 1. Okay, then as you along the length of the element, as you substitute in the zeta values, okay, it's going to be give the different points of values, so that it's going to be show the shape function like this. Similarly, when n2 becomes 1, okay, at node number 2, if you substitute the value of zeta as plus 1, then it gives the n2 which is equal to 1. Okay, then n2 value, as it is 1, it is having a distance like this, the shape variation. Then from as you substituting the other zeta values, it's going to be vary the shape like this. As you substituting, for example, if you take here, if you substitute zeta value is minus 1, then it's going to give 0, so that the variation is going to be showing like this. Similarly, at node number 3, as we substituting zeta value is 0, if you substitute here zeta value, if you substitute 0, because at node number 3 zeta value is 0, as you substituting n3 becomes 1, and as the zeta different values, if you substituting along the length of the element and the values gives, then the shape variation is going to be drawn like this. Then the overall the shape variation for 3 nodes, it is going to be q like this for one dimensional 3 noded quadratic bar element. Similarly, the shape function for 4 noded, one more internal node is added for this, so that it is also called 4 noded bar element, and also it is called cubic bar element. So these shape functions in natural coordinate system using Lagrange's interpolation functions, now we discuss. The cubic one-dimensional bar element is shown. Now you can see, as we know that the node numbering will be given for first corner nodes, then for the internal nodes, so that node number 1, node number 2, node number 3, node number 4. At node number 1, the value is minus 1. At node number 2 is plus 1. Always the element, it is going to be vary from minus 1 to plus 1. Then in between there are two nodes, node number 3 and node number 4. Then the value also you should know that. Okay, at the center the value is, it is going to be divided into 3 equal parts. Okay, this from here to here, it is the one of the parts, so that at this particular node you can get the distance from 0, it is having minus 1 by 3. The shape function of one-dimensional cubic bar element for the, by using the Lagrange's equation, that is L of k zeta, which is equal to pi n, I which is equal to 1, I which is not equal to k, zeta minus zeta I divided by zeta k minus zeta I. By using again this Lagrange's function, we can able to find out the shape functions at node number 1, 2, 3 and 4. Now consider first this is having a 4 nodes, so that n which is equal to 4. Hence, we need to find out the nodes shape function at node number 1, so that k which is equal to 1. So n1 of zeta which is equal to, here kth node will be 1, so that here zeta 1 it becomes in place of k, then remaining 3, 4. Okay. Now zeta minus zeta 3 divided by zeta 1 kth node here, so that minus zeta 3. So remaining nodes will be 3, 4, 2. So for I which is equal to 2, 4, 3, so that we are going to write it, and k will be equal to 1. So the equation becomes like this. Now substituting the all values of zeta 1, zeta 2, zeta 3, zeta 4 values. Now you can see zeta 3 value is minus 1 by 3, zeta 4 value is 1 by 3, again zeta 2 e value is plus 1. Similarly, zeta 1 value is minus 1, zeta 3 e value is minus 1 by 3, then this becomes plus 1 by 3, then zeta 1 again minus 1, zeta 4 1 by 3, again zeta 1 minus 1, zeta 2 is plus 1. So that the equation becomes like this. Hence, simplifying this, you are going to get the equation like this. Again, simplifying, the simplification gives overall the equation will be like this, and we can write n1 of zeta which is equal to minus 9 by 16 zeta square minus 1 by 9 into zeta minus 1. This is the shape function equation for node number 1. Similarly, at node number 2, we need to write at node number 2 k will be equal to 2, so that here again equation the remaining nodes the I value will be equal to 1, 3, 4. Okay, so this equation you can write zeta minus zeta 1 divided by k value will be 2, so that zeta 2 minus zeta 1, remaining 3 and 4th node you can write it the equation like this. Okay, so here kth node we need to find out the shape function. Then as we substituting zeta 1, zeta 2, zeta 3 values, the equation becomes like this. Okay, then as we simplifying, we are going to get the equation 9 by 16 zeta square minus 1 by 9 into zeta plus 1. This is the equation for the shape function at node number 2. Similarly, at k at node number 3, the kth node, okay, will be equal to 3, third node, so that n3 of zeta which is equal to, then here k becomes 3 and I becomes 1, 4, 2. So writing the equation for 3 nodes, then this gives the equation like this, and substituting the values of 1, zeta 1, zeta 2, zeta 3, zeta 4. Okay, is going to be gives like this, and simplifying, just we are going to get the equation 27 by 16 zeta square minus 1 into zeta minus 1 by 3. This gives the shape function at node number 3. Similarly, at node number 4, then the value of k will be equal to 4. Remaining high values will be 1, 3, 2. Okay, the kth node is 4, and the high nodes will be 1, 3, 2. So as we substituting again zeta 1, zeta 2, zeta 3, zeta 4 values, we get the equation like this, and simplifying again we are going to get the equation minus 27 by 16 zeta square minus 1 zeta plus 1 by 3. Now we have got all the shape functions at node number 1, 2, 3, 4. Then how it is going to be vary shape for 4 noded a cubic element we can see it. Now from the equation number 1, okay, that is the shape function n1 which is equal to, we have got this equation n1. Here if you substitute n1 value as minus 1, then the value you are going to get 1 only. As you substituting the value minus 1, then you are going to get n1 which is equal to 1. As you substituting the values of zeta in different points at different values, and it is going to be show the variation like this. At node number 3 again it will be equal to 0. At node number 4 again it will be equal to 0. At node number 2 again it will be equal to 0. That is, we know, that is what the property of the shape function. If it is one node, it is having a unity, then remaining all other nodes, the shape function will be equal to 0. Okay, this is how the variation it is going to be takes place. Similarly, as you taking node number 2, at node number 2, n2 which is equal to 2, 1, as you substituting the in n2 equation, the zeta value is plus 1, then again as we simplifying, you are going to get the value which is equal to 1. Then again at different points, if you substitute the zeta value, then again it's going to be give n2 value at node number 4 is 0, at node number 3 is 0, at node number 1 is 0. Okay, that is what the property it is going to be satisfying. Now similarly at node number 3, in the third node, the shape function equation, if you substitute the node number value, that is zeta value minus 1 by 3, then you are going to get n3 which is equal to 1. Okay, then as you substituting remaining other distances values of zeta, then you are going to get the variation like this. Okay, again you can see here at node number 1, at node number 4, at node number 2, again the n3 value will be 0. Okay, only at node number 3 it is having a 1. Similarly, the node number 4 is going to be get the n4 value is 1, and remaining all nodes it is going to be have a 0. So that it is going to be satisfying the first property of the shape.